Hi friends, welcome back to my channel. Today I will be explaining what is an ergodic random process from a conceptual point of view. And I will be using my good old example. I'm driving this particular car from my home to office and I'm interested in the displacement felt by my wheels. Actually, I'm riding my vehicle on a rough road and I'm measuring the displacement felt by my wheels on 3 days. And see, it happens to be something like this. Every day, different response. And I told you this can be modeled as a random process because there are a lot of parameters that are influencing this process. That's why it is random. That's why I'm not sure about the shape it will assume on day 4, and I'm not sure for a given realization or for a given ensemble what will be the displacement my wheel will feel at a different instant of time. So these are because of the n number of parameters like tire pressure or the temperature on that day, the ability or the skill level of the particular driver. All these things will influence the displacement that felt by these wheels, and that's why they are called random process. Now the next important question is, what is an ergodic random process? Let's try to explain that with an example. Now let me ask you a question. Here in this particular graph, I have plotted the displacement that I measured on a given day with respect to time. So I'm measuring the displacement every second. So the first second I measured a displacement of 2 mm. Similarly, for the second I measured displacement of 4 mm, and like that this goes on. For the fifth second I measured something like 2 mm. And now I am asking you, what will be the displacement felt by my wheel on corresponding to 6th and the 7th second? Hold your thought. So you need to give me the values. You know that there is some physics that governs this whole process, but because of the complexity and because of the number of variables that are involved in this particular problem, you really don't know what will be the displacement. Okay, but you can guess at least. And most probably, you will tell me a value in the range of 1 to 10 mm. Why? Because all the earlier values are around that range. I never told you my displacement will assume a value of 1000 mm. Because this is unrealistic. Or the series of data was something like 4, 2, 3, 5, like that it was. So you will never ever tell me a number some of the order of 1000 or 100. Getting it? Still now, you may not be knowing the physics or the rule which governs this process completely, but you know what is the range of values that it can assume. Got it? So, you're making a hypothesis. Knowingly or unknowingly, you are making a hypothesis that with a sufficiently long sequence, you will be gaining more insight into the problem and thereby to the physics. Let's say you assumed a displacement of 3.5 corresponding to the 6th second, and you assumed a displacement of 2.5 mm corresponding to the 7th second. So this particular process which you just now did, you did it by assuming that, or you predicted these values on the background of this particular set of values which I provided to you. This was just a single realization or a single ensemble function you can call. So using that data you predicted these two values. Getting it? So now we get into the formal definition of an ergodic process. In one single sentence, if I want to tell you what is an ergodic process, it is just simply a technique to simplify the problem or to simplify a random process. wherein a random process is said to be ergodic if its statistical properties can be deduced from a single sufficiently long random sample of the process. What you just did just now. You looked at the first 4 or 5 values and then you predicted what will be the displacement of the wheel corresponding to the 6th and the 7th second. So it is just a technique to simplify the problem involving random processes. See, the power of this assumption is huge because from a single realization or from a single random sample of the process, you will be able to deduce the statistical properties. And if you have a doubt what are the statistical properties, you can compute the mean, you can compute the autocorrelation. All these things can be done from a single sufficiently long random sample of the process. Now, let's look at another definition which is given in the dictionary. I bring your attention to this particular sentence. See, it is a process in which every sequence or sizable sample is equally representative of the whole. Got it? So that's what you just now did. I gave you a sizable sample. I gave you the displacements corresponding to the first 5 seconds and asked you to predict what will be the displacement corresponding to the 6th and the 7th second. And what hypothesis you brought in when you predicted those two values? You thought the single realization which I gave you is a representative of the whole process, and then you went ahead. Got it? Now let's get into the mathematical nitty-gritties of the definition. Now we are heading towards a more formal definition of a ergodic random process. So let's unravel things. So the same example, these are the 3 different sample functions that I have got, and this can be seen as a collection of random variables indexed with respect to time. Let's say this is t1, t2, t3. So these are the different values that this random variable corresponding to this time, it assumes these 3 different values. So a random process is a collection of such sample functions. Now, in order to characterize this, there are a lot of statistical parameters. I have defined a few of them in my earlier videos. I will simply revise those things. A few of them are given here. First one among them is a ensemble average. Ensemble averages are taken or computed over different samples. So here xk correspond to this particular index, So this is x1 of t, x2 of t, x3 of t. So the index k corresponds to that. So this is my mean. This is how it is computed, pretty straightforward over different n samples, and this is how my second order autocorrelation function is defined. And going ahead, this is how my third order autocorrelation function is defined. Simple, you keep multiplying terms and then you will end up with a higher order autocorrelation averages. Make sense? So these are defined at every time instant. That's why in the function argument you can see a t1. These are defined at every time interval or every time instance. For a process to be stationary, I have explained this in my earlier videos. Let's say if you want your process to be strongly stationary, then your mean should be same at different time instances, and your second order autocorrelation function should be same with respect to time, and similarly your third order autocorrelation function should be also a function of just the time shift, not t1. It is just a function of the time shift. It is not a function of t1. So these are all we have seen in my earlier videos. Now let's define what is called temporal averages. The key difference between a temporal average and ensemble average is, for computing temporal averages, you just need one sample function as shown over here. If you have one sample function, then you can define the mean corresponding to that particular. That means that particular means that kth sample function like this. This is the formal definition how mean is computed. Pretty straightforward. Similarly, corresponding to that particular realization or corresponding to that particular sample function, you can define the autocorrelation function, temporal autocorrelation function like this, where limit t tends to infinity is it is just a formal definition where you assume the function to be non-periodic and assuming it ranges from minus infinity to plus infinity. Again, as you can see, the definition looks more or less the same. The only difference is in ensemble averages, you are averaging it across different ensembles, but when it comes to temporal averages, you are taking the mean for one single sample function. And let's say something interesting happens now. I had sufficiently large number of sample functions. So initially I computed my ensemble averages. Then all of them turned out to be independent of the time instant at which I was evaluating them. All the higher order including the higher order autocorrelation. That means the process is strongly stationary. Okay, that aspect is done. Then I went ahead and took each of the sample functions and computed these averages as shown here. I computed the temporal averages. The process is already stationary. Now I went ahead and computed the temporal averages. Then I came to know that, or I saw that all these averages are the same across different sample functions. Interesting. This kind of random processes are called ergodic. Why? Because with knowing just one sample function, I can calculate my temporal averages. And since the process is already stationary, these temporal averages, whatever I have calculated using one single sample function, they will be equal to my ensemble averages also. So clear? So with one single sample function, I am able to compute all my statistical properties. One thing to remember is that all ergodic processes are stationary, but all stationary processes are not ergodic. If you need an ergodic process, initially it has to be stationary. Then only it can be ergodic. Please keep that thing in mind. So this simplification essentially helps us to study the whole random process with one single time history or with one single sample function. That's how this assumption or this whole assumption of ergodic process helps us in dealing with random processes. Thanks for watching.